Here's a picture of one of the amplifiers that you've been building in the lab. And you can see here's the transistor, here's the transistor. So you see this is three transistor stages. Here's a penny to give a reference on the size. So this is basically a discrete amplifier. So you have all these discrete components and then they're wired together on a board or whatever. So now we want to talk about integrated. So now here is a penny and here is a little chip, and you can kind of see the little wires connected, and so this is already a fraction of it, but then the chip itself is a lot smaller, and then here is the circuit for that chip, and you could see all these different transistors on there. And so this has lots and lots more transistors than your stage does. And so this is the concept of an integrated circuit. So we could put a whole bunch of components packed down really small. Here is a picture, a microscope picture of that image. Here are the wire connections going out, and here are all the components. So this is called an integrated circuit where everything is integrated all small. So the first thing we want to notice about it is let's look at some of these components. So this component right here is this capacitor. But this is only a 15 picofarad capacitor. If I wanted to make like a microfarad capacitor, it's going to be way bigger than the whole chip. So it gets very hard to make these capacitors. But then if I look in here, oh, here's a little transistor. So you see that the transistor itself is smaller than the capacitor. And let's see, here is, I think this is a resistor. So this whole thing to make that one resistor. So you see, in order to do this transistor compared to that resistor, I could fit in a whole bunch of transistors over the same area that it takes to do a resistor. So this is where we're getting into integrated circuits. So when we're doing integrated circuits, we want to eliminate capacitors and eliminate resistors whenever possible and replace those with transistors. Now let's look at, now when we do this technology, they call them technology paths or whatever. And so this talks about the different technologies. And so this is talking about the length of the transistor. So this one's a 0.8 micron all the way down to a 28 nanometer. And this is talking about the length of the transistor. And as we shrink these transistors down, you see that the mu NC ox is going up. And it goes up because this oxide layer gets smaller. So that gives me more capacitance per surface area because my thickness gets really small. But the problem is that I have to use a smaller and smaller operating voltage. Otherwise, it'll arc through that very thin layer. The other thing is VA, which is basically your lambda or your early voltage. You see it gets smaller and smaller as those lengths get. So we get a higher lambda. We have to operate a smaller voltage because we have these smaller devices. So just to get an idea of this, so first of all, here's kind of showing a layout of two transistors where all these different colors are different dopings and regions, and you can see that these are your connection points. So this is going to be like gate, drain, and source. I'm not sure which one's which. Okay, and then if we actually look at it, oh, so here is a small transistor. So this one is with a 40 nanometer gate. So this is your gate right here. Here is your drain and here is your source. So you see the full width all the way across here is like 500 nanometers. So if we go back to our penny analogy, when we looked at our penny, that means of these transistors, I could put 32,000 transistors across the width of that penny. And then if I wanted to go the full area, you know, you're in the billions of transistors over the area of a penny. So just to review, when we do these integrated circuits, we want to eliminate capacitors and resistors and just have transistors. And then we can integrate everything together, and those